Hello students, this is Anjana from Computer Science Department. In this class, we are going to discuss about exclusive OR function. Now let's get into our topic. Here, basically, we are having two other types of digital logic gates, which although they are not a basic gate, their own right as they constructed by combining together. But here, whenever you are going to use the logic gates, their output boolean function is not an important enough. Why? Because it should be considered as a complete logic gates. Here, these two hybrid logic gates, we can say these two hybrid logic gates as exclusive OR gate or exclusive NOR gate. Okay, if it is an exclusive OR gate, simply this is the figure for that. If it is the exclusive NOR gate, simply in front of that, if you keep a bubble like that, then it is the symbol for the exclusive NOR gate. Here, why you are going for this logic gates is justly to solve the boolean function. Why? Because it is important enough to be considered as a hybrid logic gate. So we are saying it as a exclusive OR gate. See, if you are having some boolean function like a is a plus b, so we have to construct a logic gate for that. Suppose if you are taking it as a is equal to 1 or b is equal to 1, that is you have to take the choice for either a or b. Instead of for that, you have to use this type of gates. Suppose if a is equal to 1 and b is equal to 1, or both a plus b is equal to 1, then the output from the digital gate must be also the logic level. It should be also the 1. Because of this type of logic gates, we are also having the inclusive OR function, and the logic gate these logic gate get its name from the it is having some fact tables. We are having that fact table for and function or function, just like that for this exclusive OR and exclusive NOR function also we are having the fact. Okay, then this logic gate gets its name from the fact that includes the case of q is equal to 1 when both a and b is equal to 1. But if however if the logic input is equal to 1, it is obtained only when a is equal to 1. If suppose if it is a is equal to 1, you have to take the value of a. Simply you can take this exclusive OR gate, but not both together. If you are going to take both, then simply you go for the OR gate. That is, whenever you are going to perform the addition operation, then simply in previous classes we have already discussed about that. Simply we can go for that OR gate. But if you are taking either A or B, then you have to use this exclusive OR gate. Okay. So if however a logic input is equal to 1 and it is obtained when only a is equal to 1 or only when b is equal to 1, but not both together at the same time, giving the binary inputs either 0 1 or 1 0, then the output definitely the output will become 1. So this type of gate we can say it as a exclusive OR gate or function 1 or more, commonly XOR function for short. This is because its Boolean expression includes or both case of q is equal to 1 when both a and b is equal to 1. So if however a logic input is equal to 1 and it is obtained when only a is equal to 1, then from that we can say together at the same time, giving the binary inputs of 0 1 or 1 0, then the output will be 1. This type of gate we can say it as a exclusive OR function or more commonly an XOR function for the short. So this is the because of the Boolean expression. So if you are going to take the both in case of q is equal to 1 when both a and b is equal to 1. In other words, the output of the exclusive OR gate only gives the high input when two input terminals that are different, the logic gates when respect to each other. Suppose if it is an odd number of the logic gate, then once on the inputs. If you are going to take it as like that, then if it is exclusive OR operation means either a into b or b into a, just like that we have to say. Then these two inputs can be uh, kept at the logic level 1 if it is at the logic level 1, and at the logic we are having two choices here. You can kept at the logic level 0 and you can kept at the logic level 1. So by using this, then we can solve this Boolean expression like a XOR b. This is the symbol for exclusive OR operation. Simply we can say it as XOR. So XOR B, A XOR B is the, if it is A XOR B operation, we have to perform A into B plus B into A. This is the operation that we have to perform when you are going for the exclusive OR. So in exclusive OR gate function, the XOR is too short for that. So, and it is suppose if it is going to achieve for combining the standard logic gates together to form the more complex gate functions that are used, but extensively, if you are going to build the arithmetic and logic circuits. So if it is a computational logic or comparators and error detection circuits, in these types of circuits we have to go for the, definitely you have to go for the exclusive OR function. So the two input exclusive OR gate is basically a Madlow two adder, since it gives the sum of two binary inputs. It is giving the two binary inputs, and as a result a more complex in design than the more basic type of logic gate. Suppose in truth table the logic symbol and the implementation of two input exclusive OR gate, if you are going to give the exclusive OR gate symbol, then this is the figure for that. So this is the symbol for the exclusive OR gate. Here you are giving the two inputs. This is A and this is B. Here this is the output that we are getting here. So we can say it as a two input XOR gate. Here this is a Boolean expression for that. This is A XOR B. So for that what we have to perform is A B bar plus B A bar. A XOR B means A B bar plus B A bar. So then the truth table for this XOR operation is, suppose if the value of A is 0 and the value of B is 0, then the output is 0. So that is, if it is A XOR B, then definitely the output will become 0. If it is 1 XOR operation 0, that is if the value of A is 1 and the value of B is 0, that is A XOR B. In case of A is equal to 1 and B is equal to 0, the output will become 1. In case of A is equal to 0 and B is equal to 1, that is A XOR B, that is 0 XOR 1, the output will become 1. In case of both A and B is equal to 1, then 1 XOR 1, then the output will become 0. So A and A or B but not both gives the value Q. Okay. Here this is the giving, this is the Boolean expression here, that is A B bar plus A bar B. This is a digital logic exclusive OR gate. See, this is a symbol that for the exclusive OR gate, simply just as the AND gate. It is looking like an AND gate, but it is not an AND gate. This is XOR gate. In front of that, this is the symbol that we are placing here. This is, here we are giving the two inputs. So here we are giving the two inputs. So we have drawn two lines here. Here this is the input A and this is input B. The output that we are getting here is Q. So this is the digital logic exclusive OR gate, and the Boolean expression for this is A B bar plus A bar B. So here this truth table shows whatever the truth table that we have seen previous, it is showing that the output of the exclusive OR gate only goes high when both of its two input terminals are different. See, whenever it will go high means, here the both of the input terminals are only when both the input terminals are different, that is it should not be same. That is if the value of A should not be equal to the value of B, then only the value will become different. Suppose that both the values are same, it will not be a different. Okay. So here what they are saying is, the truth table above shows the output of the exclusive OR gate only goes high when both of its two terminals are different and the logic gates with respect to each other. So if these two inputs A and B are both at logic level 1 or both at logic level 0, the output is definitely 0. So making the gate at an odd but not at the even gate. In other words, the output is 1 when there are an odd number is ones in the inputs. So the ability of the exclusive OR gate to compare the two logic levels and produce an output value, it's depending upon the input condition and is very useful in the computational logic circuits, as it gives A XOR B is equal to A B bar plus B A bar. So based upon the ability of the exclusive OR gate, we are going to compare the logic levels. Why? Because to produce an output value, this output value definitely depends upon the input condition, and it is very useful in the computational logic circuits as it gives the following Boolean expressions. See, these are the Boolean expressions that we are going to get after computing. So when you are saying it is different, the input should not be equal. The input should be input terminal should be different. At that time only it should goes high. Why? Because the logic levels with respect to each other is should be different, and if these two inputs A and B are both at the logic level 1 or at the logic level 0, but even the gate, in other words, the output is 1 when there are an odd number if 1 in the input. So either 1 or 0 it should be, either 0 or 1 it should be, but it should not be 0 both and it should not be 1 at the same time. Why? Because we are having the ability of the exclusive OR gate to compare the two logic levels. We should have to compare the two logic levels to produce the output value dependent upon the input condition, and it is very useful in the computational logic circuits as it gives us the following Boolean expressions. Okay. So this is a logic function implemented by the two input XOR. If A or B but not both will give an output Q, in general, an XOR gate will give an output value of the logic 1 only when there are an odd number of ones on the input to the gate. If these two numbers are equal, then definitely the output will become 0. In the previous slide we have already discussed that if it is different, then the input should not be equal. Okay. The logic function implemented by two input XOR is given as either A or B, but it should not be both, and it will give an output at Q. In general, an XOR gate will give an output value of logic 1 when there are an odd number of ones on the input to the gate. If these two numbers are equal, then the output is 0. Then an XOR function with more than two inputs is called OR function. Or the modulo 2 sum is not an XOR gate. This description can be expanded to apply to any number of individual inputs as shown below for a 3 input XOR gate. In the previous slide we have seen the two inputs exclusive OR gate. Here now we are going to see how it will be the 3 input XOR gate. But in this 3 input XOR gate, the XOR function with more than two inputs is, we can say it as a odd function or modulo 2 sum function. It's not an XOR. So this description can be expanded to apply any number of individual inputs. But A or B, we can take the input A or B, but not both. Why? Because it will give an output Q. So in general, an XOR gate will give an output value of logic 1 only when there are an odd number of ones on the inputs to the gate. If the two numbers are equal, the output will become 0. So A or B but not both will give an output Q. In general, XOR gate will give an output value of logic 1 only when there are an odd number of ones on the inputs to the gate. So this is about the 3 input XOR function. See, this is the figure, 3 input XOR gate. Here you are giving in the previous slide we have seen the 2 input XOR gate. This is the 2 input XOR gate. Okay, this is the 2 input XOR gate. Here we are taking the 2 inputs A, B. This is the input A, B, and this is the output Q. So this is a Boolean expression that we are going to get here. Now let us see about this 3 input XOR gate. This is a 3 input XOR gate. This is the Boolean expression for that. A XOR B XOR C. That is the output expression we will get is A bar B C plus A B bar C plus A B C bar. Just like that we are going to get. Okay. Plus A bar B bar C plus A B bar C bar plus A bar B C bar plus A bar B bar C bar plus A B C. This is the output that we are going. This is the combination of A B C. That is we are from this we will get eight outputs we are going to get here. See, this is A and this is B and this is C. Here this is the output Q. So if the value of A is 0, If the value of B is 0, if the value of C is 0, then the output will become 0. Okay. Then if the value of A is 1, value of B is 0 and the value of C is 0, then the output will become 1. Okay. This is A bar, B bar, C bar. This is A, B bar, C bar. Just like that. We have to assume like that. If the value of A is 0 and the value of B is 1, the value of C is 0, then the output will become 1. If the value of A is 1, if the value of B is 1 and the value of C is 0, then the output will become 0. If the value of A is 0, value of B is 0, value of C is 1, then the output will become 1. If the value of A is 1, if the value of B is 0, if the value of C is 1, then the output will become 0. Okay, if the value of A is 0, if the value of B is 1, if the value of C is 1, then the output will become 0. If A, B, C, if these three values are equal to 1, then the output will become 1. If the three values are, if A, B, C is equal to 0, then the output will become 0. Based upon the inputs, we'll get the output. If it is a 2 input XOR gate, we'll get 4 inputs. If it is 3 input XOR gate, we'll get 8 inputs. That is, the number of output we are going to get is 2 power n. That is, the n is the number of inputs that we are going to give. Okay. This is a 3 input XOR gate. See, this is a observer. This is a symbol. A, B, C. These are the inputs, and this is the Q. This is the output that we are getting here. These are the possible number of inputs that we are giving here, and these are the possible number of outputs that we will get here. Any odd number input, what is the any number of any odd number input, it will gives the output Q. So here the symbol that is used to denote an exclusive or odd function is, it is slightly different to that for the standard inclusive OR gate. Here the logic or the Boolean expression given for the logic OR gate is that of the logical addition, which is denoted by the standard plus sign. Here the symbol used to describe the Boolean expression, an XOR function, it will use the plus sign. Within a circle, we are going to indicate the exclusive OR symbol. That is, we are plus inside a circle. Okay. This is the symbol for the exclusive OR function. So the exclusive OR symbol also represents the mathematical direct sum of sub-objects expression. So within the resulting symbol of an exclusive OR function, beginning given as a, this is the symbol for that. We said previously that the exclusive OR function is not a basic logic gate, but the correct combination of different, it is a correct combination of different logic gates connected together. By using the 2 input truth table above, we can expand this exclusive OR function to a plus b into a into b, which means that we can realize this new expression by using this following individual gates. Now let us see what are the individual gates here. This is the AND gate, this is the AND gate, and this is the this is the OR gate, and this is the AND gate. In front of this we are having bubble, so this is NAND gate. In front of this gate we are not having any bubble, so this is AND gate. So this is the combination of XOR. By this we will get this XOR gate circuit. See, here we are giving the 2 inputs. This is A plus B. What is the XOR gate for the 2 inputs? A dash B plus B A dash. So for that, from this we can write like A plus B into A into B. Okay. For that, how we are going to construct the logic circuit here? For A plus B, this is the logic gate. For plus we are using the OR gate. For multiplication we are using the AND gate. So this is the circuit that we have designed for this A plus B into. For this we have to use the multiplication operation. So for these two we have to use the multiplication operation. No, For that we have used this AND gate. So why did you observe why you have used NAND gate here? A into B whole bar. So for that we have used this NAND gate. Okay, this is the XOR gate equivalent circuit. From this we can draw this XOR gate equivalent circuit. Okay. So one of the main disadvantages of implementing the XOR function is it contains three different types of logic circuits. See, here we are having the three different types of logic circuits. This is one is OR gate, one is NAND gate, and one is AND gate. Here we have to use three different types of logic gates, that is OR, NAND, and AND. So within its design, so one of the easier way of producing XOR function from its single gate is to use the old favorite, the NAND gate, as shown below. See here in this type of implementing, we have to use the three types of logical gates here. But instead of using this many types of logical gates, we can use the simplest. We can use the simplest way. Now let us see in the next slide. Okay, this is the here we instead of using different types of gates, here we have used here you have used only one gate, that is NAND gate. See here A bar B plus A B bar. Just like this also we can write now A bar B. For that A bar B, how you have written A bar. This is A bar. This is not a B. So this is not B bar. So we have taken this one. And again plus, for that plus we have to use this one A B bar. So this is the output. For that output we are using the plus no. So for that we are using this NAND gate. So by simply using this NAND gate, we have completed this XOR circuit without using different types of NAND gates. So here the exclusive OR gates are mainly used to build the circuits that are going to perform the arithmetic operations. And the calculations, especially odd adders, half adders, as they can provide a carry bit function. So as to control the inverter, where are more than one input passes. So the binary data and other input is supplied within the control signal. So see, if you observe this one, commonly available digital logic XOR and integrated chips, it will include. See, this is the one input and this is another input here. This is a NAND gate that we are using here. So this is NOR gate. Okay, by using this NOR gate, this is a quad 2 input exclusive OR gate. How we are going to construct this exclusive OR gate here? See, this is a 0 1 from 1 2 3 4 5 6 up to 14 inputs we are having here. This is ground level. This is a bit Q2. This is A2, B2. This is Q1, and this is A1 and B1, and this is Q3. This is B3, and this is A3. This one is Q4. This one is B4. This is A4, and this is VCC. Just like this, we are going to design this circuit. Here, the exclusive OR logic function is very useful circuit that it can be used in many different types of computer. See, it is mainly used in different types of computational circuits, although it is not a basic logic gate in its own right. Its usefulness and versatility has turned into a standard logical function complete with its own Boolean expression, operator, and symbol. Here the exclusive OR gate is widely available as a standard quad input. So based upon this package, it is going to observe how it is going to take the inputs here. It is going to take the many in different types of computational circuits. Although it is not a basic logic gate in its own right, but its usefulness and versatility has turned into the standard logic function complete with its our own Boolean expression. Here, based upon the operator and symbol, the exclusive OR gate is widely available as a standard quad 2 input based upon its package. See, the exclusive OR logic function is a very useful circuit that can be used in many different types of computational circuits, although not a basic logic gate in its own right. It will become widely available as a standard 2 input. So this is a gate or 403 CMOS package, we can say like that. So here the exclusive OR application is one of the most commonly used application is the basic logic comparator. It is one of the basic widely used application here. And the output when its two input bits are equal, Because of this, the exclusive OR gate has an inequality status being known as an odd function. So, in order to compare the two numbers that contain these two or more bits, the additional exclusive OR gates are needed for the logic comparator bits wide. So, in the from this we can say that the mainly used applications are the basic logic comparator, which produces the logic output when its two inputs are not equal. Because of this, the exclusive OR gate has an inequality status, so being known as the odd function. In order to compare the two functions that contain the two or more bits, additional exclusive OR gates are needed. Okay, these are the this is about exclusive OR gate and the applications of the exclusive OR gate.